Welcome to this gentle exploration of the universe's most magnificent force, where celestial bodies dance through the cosmos in patterns so precise they've inspired poets and guided civilizations for millennia. Tonight, we drift into the story of gravity, that invisible choreographer that shapes everything from falling raindrops to spiraling galaxies, orchestrating a ballet that has played without pause for nearly 14 billion years. As you settle into this quiet moment, perhaps you're watching the evening sky deepen into darkness, or maybe you're listening during a peaceful afternoon break. Wherever you find yourself, know that you're witnessing gravity's artistry in every moment. The gentle pull that keeps you grounded, the moon's slow arc across the heavens, the very breath flowing through your lungs, all participate in this cosmic dance that connects every grain of sand to every distant star. If you find comfort in these soft-spoken journeys through science, I invite you to subscribe. How was your day? Wherever you are in the world, whatever time it is, I'm really glad you're here. If you feel like it, comment your time and location below. It's always amazing to see how far and wide we're connected, even as we wind down together. Tonight, or today, you're going to drift gently into a story that begins 93 million miles away, on the surface of our sun. This video explores how solar flares, massive bursts of energy from our nearest star, can shape the world we live in. From lighting up the skies with auroras to disrupting satellites and power grids, these invisible storms remind us that space isn't silent, it's alive. You'll learn how solar flares form, how they affect Earth, and what we're doing to predict and protect ourselves from them. The visuals are here if you want to watch, but feel free to just close your eyes and listen. Let your thoughts travel to the edge of the solar wind, and let's begin. The universe holds countless wonders, and we have all the time we need to explore them together at a pace that soothes rather than overwhelms. Tonight, we begin our story not with equations or complex theories, but with a simple truth that would have astonished our ancestors. Right now, as you rest in the comfort of your surroundings, you are traveling through space at extraordinary speeds. Earth spins on its axis at over 1,000 kilometers per hour, while simultaneously racing around the sun at 30 kilometers per second. Our entire solar system sweeps through the Milky Way at 220 kilometers per second, and our galaxy itself drifts through the cosmic web at 600 kilometers per second. Yet you feel perfectly still, cradled in gravity's gentle embrace. This is the profound elegance of our cosmic dance, so vast and smooth that we experience only peace within its rhythm. But how did this magnificent choreography begin, and what invisible hand guides the steps of planets, moons, and stars as they waltz through the endless night? The story unfolds in the early universe, when space itself was far denser and hotter than anything we can imagine today. In those first moments, after the Big Bang, tiny quantum fluctuations, whispers of uncertainty at the smallest scales, would become the seeds of all the structure we observe around us. These microscopic ripples in the fabric of space-time were stretched to cosmic proportions during a brief period called inflation, creating a universe that was almost perfectly smooth but not quite. Into this nearly uniform cosmos, gravity began its patient work. Where matter was even slightly denser, gravity's pull grew stronger, attracting more material from the surrounding regions. Where matter was slightly less dense, it became even more rarefied as its contents drifted toward the denser areas. This process, playing out over millions of years, gradually transformed the universe from a smooth, featureless expanse into the rich cosmic web we observe today. The first stars ignited in this slowly evolving landscape, born from the gravitational collapse of vast clouds of hydrogen and helium. These stellar nurseries were not randomly scattered, but followed the invisible threads of dark matter that had begun to define the universe's architecture. Dark matter, that mysterious substance that outweighs ordinary matter 5 to 1, formed the scaffolding upon which all visible structure would eventually hang. As these primordial stars lived and died, they enriched the cosmos with heavier elements forged in their nuclear furnaces. Carbon, oxygen, silicon, iron, all the ingredients necessary for rocky worlds and complex chemistry, were scattered into space by stellar winds and supernova explosions. Gravity gathered these enriched materials into new generations of stars, and around these younger suns, the first planetary systems began to form. The formation of our own solar system exemplifies this cosmic choreography on a more intimate scale. Nearly 5 billion years ago, within a slowly rotating cloud of gas and dust, enriched by countless generations of stellar evolution, gravity began to concentrate material at the center. As this central region grew denser and hotter, the surrounding disk of matter began to coalesce into the building blocks of planets. The process was surprisingly gentle at first. Microscopic grains of dust, no larger than particles of smoke, would encounter each other in the cosmic darkness and cling together through electrostatic forces. These growing clumps attracted more material through their own modest gravitational pull, gradually building larger and larger bodies over millions of years. It was a patient process, requiring immense spans of time to transform cosmic dust into mountain-sized planetesimals. But even as these early building blocks formed, they were already beginning to dance. The conservation of angular momentum, the same principle that causes figure skaters to spin faster when they pull their arms inward, meant that as the solar disk contracted, it spun faster. This rotation naturally flattened the disk into a thin plane, establishing the stage upon which all future orbital choreography would unfold. Within this spinning disk, gravity began to play favorites. The most massive concentrations of material attracted more and more matter, growing into what we now recognize as the planets. Their growth wasn't uniform or peaceful. The early solar system was a violent place, filled with catastrophic collisions that would reshape worlds and scatter debris across vast distances. The Moon itself is thought to be the result of one such collision, when a Mars-sized object struck the young Earth and flung molten rock into orbit. Yet even in this apparent chaos, the fundamental laws of physics were quietly establishing order. Each collision, each gravitational interaction, was governed by the same principles that would eventually create the stable, predictable orbits we observe today. The planets weren't just forming, they were learning to dance, finding their rhythm in the cosmic ballet that gravity had choreographed. As the solar system matured, the dance became more refined. Jupiter, the massive giant, emerged as the system's primary gravitational conductor. Its immense mass influenced the orbits of every other body in the solar system. Its gravitational pull helped clear the asteroid belt, prevented the formation of a planet between Mars and Jupiter, and even influenced the delivery of water to the inner planets. In many ways, Jupiter served as both protector and destroyer, shaping the solar system's architecture through its gravitational dominance. The smaller planets, meanwhile, settled into their own unique rhythms. Mercury, closest to the Sun, races through its orbit in just 88 Earth days, while distant Neptune takes 165 Earth years to complete a single lap. Each world found its own tempo in the cosmic symphony, their orbital periods determined by their distance from the Sun and the immutable laws of celestial mechanics. This gravitational choreography extends far beyond our familiar solar system. Throughout the galaxy, countless other planetary systems follow similar patterns, their worlds locked in orbital resonances that create mathematical harmonies across the cosmos. Some systems are even more tightly choreographed than our own, with chains of planets maintaining precise relationships that have persisted for billions of years. The Milky Way itself participates in an even grander dance. Our galaxy rotates slowly, taking our solar system on a journey around the galactic center that requires 225 million years to complete. Since complex life first appeared on Earth, we have completed less than 3 full orbits around our galaxy's heart. We are passengers on a cosmic carousel, spinning through space at speeds that would make any earthbound ride seem practically motionless. At the center of our galaxy lies a supermassive black hole, an object so dense and gravitationally powerful that it warps space-time around it like a cosmic whirlpool. This invisible giant, containing the mass of roughly 4 million suns compressed into a space smaller than our solar system, anchors the entire galactic structure. The stars near the galactic center orbit this black hole at tremendous speeds, some completing their elliptical paths in just a few decades. But even our entire galaxy is not immune to gravity's greater choreography. The Milky Way belongs to what astronomers call the local group, a collection of more than 50 galaxies bound together by their mutual gravitational attraction. The largest member of this cosmic dance troupe is the Andromeda Galaxy, a spiral galaxy even larger than our own, located about 2.5 million light-years away. Despite this enormous distance, gravity is slowly but inexorably pulling our two galaxies together. In approximately 4 billion years, the Milky Way and Andromeda will merge in a slow-motion collision that will fundamentally reshape both galaxies. This galactic ballet will unfold over hundreds of millions of years, with stars from both galaxies being flung into new orbits as the two spiral structures blend and ultimately form a single, larger, elliptical galaxy. The local group itself is part of an even larger structure called the Virgo supercluster, which contains thousands of galaxies spread across roughly 100 million light-years. And this supercluster is just one of many such structures scattered throughout the observable universe, each one held together by the persistent, patient pull of gravity. These cosmic assemblages form a web-like pattern on the largest scales, with dense filaments of galaxies connected by vast, relatively empty voids. This cosmic web represents the largest scale structure in the universe, a testament to gravity's ability to organize matter across distances so vast that light itself takes billions of years to cross them. As you drift deeper into this cosmic reverie, remember that you are not separate from this grand choreography, but woven into its very fabric. The atoms in your body were forged in the nuclear furnaces of ancient stars, scattered by stellar winds and supernova explosions, and gathered again by gravity's patient hands into the remarkable arrangement that is you. The same force that guides galaxies in their stately orbits also governs the circulation of blood through your veins, the rhythm of your breathing, the gentle pull that keeps your feet planted firmly on the ground. You are part of the dance, a temporary constellation of star stuff held together by electromagnetic forces and guided by gravity through this brief moment of consciousness. Tonight, as you prepare for sleep, carried by the Earth through its orbit around the Sun, remember that you are dancing. You are part of a performance that began billions of years ago and will continue long after the last star has faded. The rhythm is slow, the movements vast, but the dance is eternal, and gravity is both the music and the floor upon which this cosmic ballet unfolds. In the gentle pull that keeps you nestled in your bed, in the moon that pulls the tides and stabilizes our planet's seasons, in the sun that holds our world in its warm embrace, you can feel the universe itself reaching out to you, reminding you that nothing exists in isolation. Everything is connected, everything influences everything else, and the force that binds it all together is as gentle as a whisper and as powerful as the cosmos itself. So rest now, knowing that you are held not just by your bed or your surroundings, but by the very geometry of space-time, by the gravitational embrace of planets and stars, by the same force that lit the first stars and will guide the last planets in their orbits around dying suns. As we drift deeper into our cosmic reverie, carried along by gravity's eternal embrace, we find ourselves drawn toward a new chapter in the universe's story. The same gravitational forces that choreograph the dance of planets and bind galaxies in their stately procession also govern the life of our own star, that brilliant beacon we call the Sun. And it is here, in the heart of our solar system, that we encounter one of space's most magnificent and mysterious phenomena: solar flares. Picture, if you will, the Sun not as the steady, unchanging light source it appears to be from Earth, but as a dynamic, breathing entity. A massive ball of plasma, 25 times hotter at its core than at its surface, where temperatures soar to 15 million degrees Celsius. This is no gentle campfire burning in the cosmic darkness, but a nuclear furnace of unimaginable power, fusing hydrogen into helium at a rate that converts 4 million tons of matter into pure energy every single second. The Sun's surface, that seemingly smooth golden disk we see in our sky, is actually a churning ocean of superheated gas, marked by dark patches called sunspots that appear and disappear in mysterious cycles. These sunspots, some larger than Jupiter itself, are regions where the Sun's powerful magnetic field lines become twisted and tangled, creating cooler areas that appear dark against the blazing background. They drift across the solar surface like islands in a sea of fire, following patterns that have puzzled astronomers for centuries. It is from these regions of magnetic complexity that solar flares are born. Imagine invisible force fields, lines of magnetic energy that arc high above the Sun's surface like enormous transparent bridges. These magnetic field lines carry tremendous amounts of energy, and when they become too twisted, too strained by the Sun's constant motion, something remarkable happens. They snap. When magnetic field lines reconnect in the Sun's atmosphere, they release energy equivalent to billions of hydrogen bombs exploding simultaneously. This is a solar flare, a sudden brightening that can outshine the rest of the Sun's surface for minutes or even hours. The energy released travels outward in all directions, carrying with it a stream of charged particles, radiation, and magnetic disturbances that race through space at millions of kilometers per hour. But here's where our story becomes deeply personal, where the cosmic touches the intimate. These solar outbursts, born in the nuclear heart of a star 93 million miles away, don't simply dissipate harmlessly into the void. They travel across the solar system, and some of them find their way to Earth, where they interact with our planet in ways both subtle and profound. Our Earth, you see, is not defenseless against these stellar storms. Our planet possesses its own magnetic field, generated by the motion of molten iron in its core. This magnetosphere, as scientists call it, extends far into space, creating an invisible shield that deflects most of the Sun's harmful radiation and charged particles. It's like living inside a protective bubble, one that has sheltered life on Earth for billions of years. When solar flares reach our planet, they encounter this magnetic shield in a cosmic dance of attraction and repulsion. The charged particles from the Sun follow the lines of Earth's magnetic field, spiraling down toward the magnetic poles. As these particles collide with gases in our upper atmosphere, they create one of nature's most spectacular displays, the aurora. The northern lights, those curtains of green, blue, and red that shimmer across polar skies, are actually the visible signature of solar flares interacting with our planet. Each dancing ribbon of light represents millions of solar particles painting the sky as they collide with oxygen and nitrogen molecules 60 to 400 kilometers above our heads. It's as if the Sun is sending us messages written in light, cosmic correspondence, delivered across the vast emptiness of space. But the influence of solar flares extends far beyond these beautiful displays. In our modern world, so dependent on technology and electrical systems, solar activity can have surprisingly terrestrial consequences. The same magnetic disturbances that create auroras can also interfere with radio communications, disrupt satellite operations, and even affect power grids on Earth's surface. During particularly intense solar storms, astronauts aboard the International Space Station must take shelter in the most shielded areas of their craft. Airlines sometimes reroute flights to avoid polar regions where radiation levels spike during solar events. Even here on the ground, sensitive electronic equipment can be affected by the electromagnetic pulses that accompany major solar flares. Yet there's something almost poetic about this connection between stellar fury and earthly consequence. The same star that provides the energy for photosynthesis, that drives our weather patterns and makes life itself possible, occasionally reminds us of its raw power through these energetic outbursts. Solar flares are like the sun's way of stretching, of releasing tension built up in its complex magnetic field, much as we might stretch our muscles after sitting still for too long. The study of solar flares has revealed fascinating patterns in our star's behavior. The sun follows an 11-year cycle of activity, moving from periods of relative calm to times of intense magnetic activity and back again. During solar maximum, the peak of this cycle, sunspots proliferate across the solar surface and flares become more frequent and powerful. During solar minimum, our star enters a quieter phase, though it never becomes completely dormant. Scientists have learned to monitor these solar cycles carefully, using satellites positioned between Earth and the Sun to provide early warning of incoming solar storms. Space weather, as it's come to be known, has become as important to track as terrestrial weather for our technology-dependent civilization. We've developed a new kind of meteorology, one that looks not to clouds and wind patterns, but to magnetic field lines and particle streams flowing from our nearest star. The particles released by solar flares don't simply disappear after creating their earthly effects. They become part of the solar wind, a constant stream of charged particles flowing from the sun throughout the solar system. This solar wind shapes the magnetic environments of all the planets, creating comet tails that always point away from the sun and carving out the boundaries of planetary magnetospheres millions of kilometers from their surfaces. Even the moon, lacking its own magnetic field, bears the scars of solar activity. The lunar surface is constantly bombarded by solar particles, gradually darkening its soil and creating the subtle color variations visible through telescopes. Every grain of lunar dust tells a story of 4.5 billion years of exposure to our star's variable moods. As we continue our gentle drift through this cosmic narrative, consider how solar flares represent yet another example of the universe's interconnectedness. The nuclear processes at the sun's core, governed by the same fundamental forces that shape galaxies and guide planetary orbits, reach across space to touch our daily lives in ways both beautiful and practical. The aurora that might grace tomorrow night's sky began as magnetic field lines deep within the sun, twisted by convection currents and released in a burst of energy that traveled for days across the void to paint our atmosphere with light. In the grand symphony of the cosmos, solar flares are like sudden dramatic crescendos that remind us of the dynamic nature of the universe we inhabit. They connect us directly to stellar processes, making us participants in the ongoing story of our star's life. As you settle deeper into rest tonight, remember that even now, charged particles from ancient solar flares are spiraling through Earth's magnetic field, creating invisible connections between your sleeping form and the nuclear furnace that powers our solar system. The sun's magnetic heartbeat, marked by the rhythm of flares and quiet periods, provides yet another layer to the cosmic dance we've been exploring. Just as gravity orchestrates the movements of planets and galaxies, magnetic forces shape the behavior of stars and the space between them. And in this vast, interconnected web of cosmic forces, we find our small planet perfectly positioned to receive both the gentle warmth of steady sunlight and the occasional dramatic reminder of our star's immense power. Tonight, as Earth turns slowly beneath the unchanging stars, solar particles released days ago may be arriving at the edge of our magnetosphere, beginning their spiral journey toward the poles, where they will paint the sky with colors beyond description. As we drift deeper into our solar story, we find ourselves drawn toward the sun's restless nature, where beneath that seemingly steady golden surface lies a world of constant motion and magnetic complexity. The sun you see each morning, that familiar disk of light rising over the horizon, is actually a massive ball of plasma held together by its own gravity, where temperatures reach millions of degrees and magnetic fields dance in patterns so intricate they would make the most elaborate ballet seem simple by comparison. Now, you might wonder what exactly plasma is, and it's a fair question to ponder as you settle into comfort. Plasma is often called the fourth state of matter, beyond solid, liquid, and gas. It's what happens when gas becomes so hot that electrons are stripped away from their atoms, creating a soup of charged particles that responds to magnetic fields like iron filings to a magnet. Nearly all the matter in the universe exists in this plasma state, though here on our cool little Earth, we rarely encounter it except in lightning bolts or the gentle glow of a neon sign. The sun is entirely made of this plasma, and within its depths, nuclear fusion occurs at a rate that would power human civilization for billions of years if we could somehow capture just a tiny fraction of it. But it's not the fusion itself that creates solar flares, though fusion certainly provides the energy. Instead, it's the sun's magnetic field, generated by the complex motions of this charged plasma, that holds the key to understanding these magnificent eruptions. Imagine, if you will, the sun's magnetic field as an invisible web of force lines that extend far out into space, creating what scientists call the heliosphere, a vast bubble that encompasses our entire solar system. These magnetic field lines are constantly being twisted and tangled by the sun's rotation and the churning motions of plasma within its interior. The sun doesn't rotate as a solid body like Earth does. Instead, its equator spins faster than its poles, completing one rotation in about 25 days, while the polar regions take 35 days. This differential rotation is like stirring honey with a spoon, creating swirls and eddies that grow more complex over time. As these magnetic field lines become increasingly twisted and tangled, they store enormous amounts of energy, much like a rubber band that's been wound tighter and tighter. Eventually, something has to give. When the magnetic tension becomes too great, the field lines suddenly snap and reconnect in a process called magnetic reconnection. This is the fundamental mechanism behind solar flares, and it happens with a violence that defies easy comprehension. During magnetic reconnection, the stored magnetic energy is released almost instantaneously, heating plasma to temperatures of tens of millions of degrees and accelerating particles to significant fractions of the speed of light. The energy released in a large solar flare can be equivalent to billions of hydrogen bombs exploding simultaneously, though this energy is released into the near vacuum of space rather than Earth's atmosphere, which is fortunate for us. Solar flares are classified by their intensity, using a system that might remind you of how earthquakes are measured. The smallest flares are called A-class, followed by B, C, M, and X-class flares, with each letter representing a tenfold increase in energy output. Within each class, flares are further subdivided by numbers, so an M5 flare is 5 times more powerful than an M1 flare. The most powerful flares ever recorded have been X-class events that exceeded X20, representing energy releases that could power human civilization for millennia. But solar flares don't occur randomly across the sun's surface. They're intimately connected to sunspots, those dark patches that astronomers have been observing for centuries. sunspots appear dark, not because they're cold by any absolute measure, but because they're cooler than the surrounding solar surface, with temperatures around 4,000 degrees Celsius, compared to the sun's average surface temperature of 5,500 degrees. These cooler regions exist because intense magnetic fields in sunspot areas suppress the normal convection that brings hot plasma to the surface. Sunspots often occur in pairs or groups, connected by loops of magnetic field lines that arch high into the sun's atmosphere, or corona. These magnetic loops can be hundreds of times larger than Earth, creating cathedral-like structures of invisible force that channel and constrain the flow of plasma. When you see images of the corona during a solar eclipse, those graceful streamers and loops you observe are actually the sun's magnetic field made visible by the plasma that follows its contours. The sun's activity follows an 11-year cycle, during which the number of sunspots waxes and wanes in a predictable pattern. At solar minimum, the sun's surface might be completely free of sunspots for days or weeks at a time, and solar flares are relatively rare and weak. But as the cycle progresses towards solar maximum, sunspots become more numerous and complex, and the likelihood of powerful flares increases dramatically. We're currently approaching the peak of solar cycle 25, which means the sun is becoming increasingly active, and we can expect more frequent and intense flares in the coming years. The journey of a solar flare from the sun to Earth is a story that unfolds over the course of minutes to days, depending on what aspect of the flare we're considering. The electromagnetic radiation from a flare, including visible light, ultraviolet radiation, and X-rays, travels at the speed of light and reaches Earth in just over 8 minutes. This radiation is the first herald of a solar flare, and it can immediately begin affecting our planet's upper atmosphere, causing sudden increases in ionization that can disrupt radio communications, particularly at high frequencies used by aviation and amateur radio operators. Following the electromagnetic radiation comes a stream of high-energy particles, primarily protons and electrons, that have been accelerated to tremendous speeds by the flare. These particles travel more slowly than light, but still reach Earth within hours of a major flare. When they encounter our planet's magnetic field, they can cause what are known as solar particle events, which pose radiation hazards to astronauts and airline passengers flying at high altitudes, particularly over polar routes where Earth's magnetic field provides less protection. But perhaps the most dramatic consequence of a major solar flare is the coronal mass ejection, or CME, that often accompanies it. Not all flares produce CMEs, but the largest flares frequently do, hurling billions of tons of plasma and magnetic field into space at speeds that can exceed 1,000 kilometers per second. These massive clouds of charged particles can take anywhere from 1 to 4 days to reach Earth, depending on their speed and direction. When a CME collides with Earth's magnetosphere, the results can be spectacular and sometimes problematic. The interaction between the CME's magnetic field and Earth's magnetic field can cause the latter to fluctuate rapidly, inducing electrical currents in everything from power lines to oil pipelines. These geomagnetically induced currents can damage transformers in electrical grids, cause corrosion in pipelines, and interfere with sensitive electronic equipment. The same magnetic interactions that can damage our technology also create one of nature's most beautiful displays, the aurora. When charged particles from a CME are channeled along Earth's magnetic field lines toward the poles, they collide with atoms and molecules in our upper atmosphere, causing them to emit light in characteristic colors. Oxygen atoms produce the familiar green and red colors of the aurora, while nitrogen contributes blues and purples. During major geomagnetic storms, auroras can be visible at much lower latitudes than usual, sometimes appearing as far south as the Caribbean or Mediterranean. The effects of solar flares extend beyond the immediate disruption of technology and the creation of beautiful auroras. There's growing evidence that solar activity influences Earth's climate on various timescales, though the mechanisms are complex and still being studied. The Sun's total energy output varies slightly with its 11-year cycle, and this variation, combined with changes in ultraviolet radiation that affect ozone chemistry in the stratosphere, may contribute to subtle but measurable climate effects. Perhaps more intriguingly, there's evidence that solar activity may influence cloud formation through its effects on cosmic rays. When the Sun is more active, its enhanced magnetic field and solar wind help deflect cosmic rays from deep space that would otherwise reach Earth's atmosphere. Cosmic rays may play a role in cloud formation by ionizing atmospheric particles, so changes in cosmic ray intensity could potentially affect cloud cover and thus climate. This connection remains an active area of research, with scientists working to understand the complex interplay between solar activity, cosmic rays, and Earth's climate system. The biological effects of solar flares are another area of ongoing investigation. While Earth's atmosphere and magnetic field protect us from the worst effects of solar radiation, there's evidence that geomagnetic disturbances can affect living organisms in subtle ways. Some studies have suggested correlations between geomagnetic activity and everything from heart attack rates to the behavior of migratory animals, though the mechanisms behind these effects remain poorly understood. As we continue to develop a more technological civilization, our vulnerability to solar flares increases. The Great Geomagnetic Storm of 1859, known as the Carrington event after the astronomer who observed the flare that caused it, induced currents strong enough to allow telegraph operators to continue working even after disconnecting their power sources. If a similar event occurred today, it could cause widespread blackouts, satellite failures, and disruption of GPS and communication systems that our modern world depends upon. This growing vulnerability has led to increased efforts to monitor and predict solar activity. Networks of ground-based observatories and space-based satellites continuously monitor the Sun for signs of flares and CMEs, providing warnings that allow power companies to take protective measures and airlines to reroute flights away from polar regions during severe solar storms. The science of space weather forecasting has become increasingly sophisticated, though predicting exactly when and where the Sun will produce its next major flare remains challenging. Understanding solar flares also provides insights into stellar physics more broadly. Our Sun is a fairly typical star, and the processes that drive solar flares occur on other stars throughout the galaxy. Some stars produce flares that dwarf anything our Sun has ever generated, and studying these stellar flares helps us understand both stellar evolution and the potential habitability of planets orbiting other stars. A planet orbiting a highly active flare star would face a much harsher radiation environment than Earth, which could affect the development and survival of life. The study of solar flares continues to reveal new mysteries and complexities. Recent observations have shown that the Sun can produce much more powerful flares than previously thought possible, with some events releasing energy equivalent to thousands of times the most powerful flares ever recorded. These so-called superflares occur rarely on Sun-like stars, perhaps once every few thousand years. But they remind us that our seemingly stable Sun is capable of truly extraordinary displays of power. As you settle deeper into rest, perhaps you can imagine the Sun continuing its ancient dance of magnetic fields and plasma, occasionally releasing bursts of energy that race across the solar system at incredible speeds. These solar flares connect us to the broader cosmos in ways both beautiful and practical, reminding us that we live not in isolation, but as part of a dynamic solar system where the moods of our nearest star can ripple through space to affect everything from our technology to the shimmering lights that dance across polar skies. The Sun's magnetic field lines stretch and twist through space like invisible ribbons dancing in a cosmic wind, And as we settle deeper into our exploration of solar activity, we find ourselves drawn into one of nature's most elegant, yet powerful phenomena. The relationship between our star and our planet operates on scales both intimate and vast, connecting the nuclear furnace burning 93 million miles away to the very device you're using to listen to these words. Picture, if you will, the sun not as a simple ball of fire, but as a complex magnetic organism, breathing and pulsing with rhythms that have persisted for billions of years. Every 11 years, give or take, our star undergoes a remarkable transformation. Its magnetic field, that invisible architecture that shapes everything from sunspots to solar flares, completely reverses. The north magnetic pole becomes south, the south becomes north, and in this grand magnetic dance, we witness one of the universe's most reliable yet mysterious cycles. This solar cycle, as astronomers have come to call it, governs much more than academic curiosity. It's the conductor of a symphony that plays out across our entire solar system, with Earth serving as one of the most responsive instruments in this cosmic orchestra. When the sun is magnetically quiet, during what we call solar minimum, our planet enjoys a kind of space weather calm. The aurora retreat toward the poles, satellite operators breathe easier, and the invisible shield of charged particles that surrounds our world settles into a steady, predictable rhythm. But as the sun awakens from its magnetic slumber, as sunspot numbers climb and the solar surface becomes increasingly restless, we enter solar maximum. This is when our star's true power reveals itself, when the twisted magnetic field lines that have been building tension for years finally snap and release their stored energy in brilliant flashes that can be seen from instruments here on Earth. These solar flares, these sudden brightenings on the sun's surface, are not mere curiosities for astronomers to catalogue. They are harbingers of change, messengers that travel the vast distance between worlds to remind us that we live within our star's domain. When a particularly powerful flare erupts, it sends forth a cascade of energy that races through space at the speed of light. Within 8 minutes and 20 seconds, the very moment that sunlight takes to reach our eyes, this burst of electromagnetic radiation washes over our planet. The first to feel this solar touch are the machines we've placed in orbit around our world. Communication satellites, those silent sentinels that carry our voices and data across continents, suddenly find themselves bathed in radiation far more intense than their designers anticipated. Some may temporarily shut down their sensitive electronics, entering safe mode until the storm passes. Others, the unlucky few caught in the full fury of a major flare, may suffer permanent damage, their circuits fried by the sun's electromagnetic assault. But the sun's influence doesn't stop at the edge of space. High above the Earth, in the thin upper reaches of our atmosphere, solar radiation begins to heat and ionize the gases that protect us from the harshness of space. The ionosphere, that electrically charged layer that normally helps radio waves bounce around our planet's curve, becomes turbulent and unpredictable. Radio operators find their signals fading in and out, as if some cosmic hand were adjusting the volume on their transmissions. Airlines, too, must reckon with the sun's moods. Pilots flying polar routes, where the Earth's magnetic field lines funnel solar particles deep into our atmosphere, sometimes find themselves forced to change course. The radiation levels at cruising altitude can spike dramatically during a solar storm, and while the risk to passengers on a single flight is minimal, flight crews who spend their careers crossing these high-latitude routes must be protected from cumulative exposure. Perhaps most dramatically, when a solar flare is accompanied by what scientists call a coronal mass ejection, the sun doesn't just send radiation our way, it hurls actual matter into space. Billions of tons of plasma, that fourth state of matter where electrons have been stripped from their atoms by intense heat, stream away from the sun at speeds that can exceed 1 million miles per hour. This cloud of charged particles, carrying with it the twisted magnetic field lines that spawned the original flare, becomes a kind of magnetic bullet aimed at whatever lies in its path. When such a cloud encounters Earth, usually 1 to 3 days after the initial flare, the real show begins. Our planet's magnetic field, that invisible shield generated by the churning molten iron in our core, suddenly finds itself under assault. The solar wind, normally a gentle breeze of particles flowing past our magnetic barriers, becomes a gale that compresses and distorts the very shape of our magnetosphere. It's during these magnetic storms that the aurora venture far from their usual polar homes. The same charged particles that would normally be channeled harmlessly into the thin air above Alaska and northern Canada suddenly find new pathways into our atmosphere. They spiral down magnetic field lines that have been twisted and reconnected by the solar onslaught, painting the night sky with curtains of green, red, and purple light as far south as the Mediterranean or the American Midwest. These dancing lights, beautiful as they are, mark something more profound than a mere light show. They represent the moment when our sun's influence penetrates deepest into our world, when the boundary between solar and terrestrial becomes blurred. The very atoms in our upper atmosphere, excited by the impact of solar particles, give up their energy as photons of light, creating a display that can be seen for hundreds of miles. But the sun's reach extends even deeper into our technological civilization. The same magnetic disturbances that create aurora can induce electrical currents in any long conductor on Earth's surface. Power lines, stretching across continents like metallic spiderwebs, suddenly find themselves carrying currents they were never designed to handle. Transformers, those critical nodes in our electrical grid, can overheat and fail when subjected to these geomagnetically induced currents. The Great Geomagnetic Storm of 1989 demonstrated this vulnerability when Quebec's entire electrical grid collapsed in a matter of minutes, leaving 6 million people without power for 9 hours. The induced currents had found the weakest link in the system and exploited it with surgical precision. Telegraph operators in the 19th century, during the famous Carrington event of 1859, reported that their lines carried so much induced current that they could disconnect their batteries and still send messages powered by the storm itself. Some telegraph offices caught fire from the overloaded circuits. Modern financial markets, those intricate networks of high-frequency trading and split-second transactions, also feel the sun's influence. GPS satellites, upon which so much of our timing and navigation depends, can lose accuracy during solar storms as the ionosphere bends and delays their signals in unpredictable ways. A trader in London, trying to execute a transaction timed to the microsecond, might find their atomic clock synchronization disrupted by a magnetic storm triggered by an event that occurred on the sun 3 days earlier. Even our understanding of climate carries the sun's magnetic signature. While the sun's total energy output varies by less than 0.1% over the course of the solar cycle, this small change can have measurable effects on Earth's weather patterns. The Little Ice Age that gripped Europe from roughly 1645 to 1715 coincided with a period of dramatically reduced solar activity called the Maunder Minimum, when sunspots virtually disappeared from the solar surface for 70 years. The mechanisms by which solar variability influences terrestrial climate remain subjects of active research. Some scientists propose that cosmic rays, those high-energy particles from deep space that are partially deflected by the solar wind, may play a role in cloud formation. When the sun is magnetically active, its enhanced solar wind provides better shielding against cosmic rays. When it's quiet, more cosmic rays penetrate the inner solar system, potentially affecting the nucleation of clouds in Earth's atmosphere. Tree rings, those annual growth bands that serve as nature's historical record, carry within their cellulose the isotopic signatures of past solar activity. Carbon-14, created when cosmic rays strike nitrogen atoms in our atmosphere, becomes incorporated into living wood. By measuring the carbon-14 content of ancient trees, scientists can reconstruct the sun's magnetic behavior, stretching back thousands of years, revealing a star whose moods and cycles extend far beyond the 11-year rhythm we observe today. Ice cores from Greenland and Antarctica tell similar stories. Beryllium-10, another isotope created by cosmic ray bombardment, falls to Earth in precipitation and becomes trapped in layers of ice. These frozen archives reveal that the sun's activity has varied dramatically over geological time, with periods of enhanced activity creating isotopic signatures that persist in the ice for millennia. The sun's influence on our world operates through pathways both obvious and subtle, connecting the nuclear processes in our star's core to phenomena as diverse as radio blackouts and the migration patterns of birds. Some species appear to use Earth's magnetic field for navigation, and researchers have documented cases where solar storms seem to disrupt these biological compasses, causing whales to beach themselves or birds to lose their way during migration. Even human health may bear traces of our star's variability. Some studies suggest correlations between geomagnetic activity and everything from heart attack rates to psychiatric admissions, though the mechanisms behind such connections remain largely speculative. The human body, after all, is an electrical system, with nerve impulses and heart rhythms governed by precisely timed electrical signals. Whether the magnetic storms that can disrupt power grids and satellite communications also influence the bioelectrical processes within our bodies remains an open question. As we drift deeper into this exploration of solar influence, we find ourselves confronting a fundamental truth about our place in the cosmos. We are not isolated observers of celestial events, but participants in a vast electromagnetic ecosystem that extends from the sun's core to the edge of the solar system. The flares and storms we observe on our star's surface are not distant curiosities, but integral parts of the environment in which our planet exists. The sun's magnetic field, carried outward by the solar wind, creates what scientists call the heliosphere, a vast bubble of solar influence that extends far beyond the orbits of the planets. This magnetic domain, larger than our solar system itself, shields us from some of the galaxy's more energetic radiation, while simultaneously subjecting us to the sun's own electromagnetic moods. Within this heliosphere, we find ourselves in constant dialogue with our star. Every solar flare sends a message that arrives at Earth in multiple forms. First, the electromagnetic radiation traveling at light speed, then the energetic particles minutes or hours later, and finally, if we're fortunate or unfortunate enough, the massive plasma clouds that can reshape our planet's entire magnetic environment. This ongoing conversation between Earth and Sun has been taking place for over 4 billion years, shaping not just our planet's magnetic field and atmosphere, but potentially influencing the very evolution of life itself. The same magnetic field that protects us from deadly cosmic radiation is constantly being sculpted and modified by solar activity. Without the sun's influence, Earth's magnetic field might be very different, and the history of life on our planet might have followed an entirely different path. As you settle into sleep tonight, consider that you are resting within this vast electromagnetic embrace, protected by magnetic fields generated deep within our planet's core, but constantly shaped by the activity of a star 93 million miles away. The aurora that may be dancing over polar regions at this very moment are writing temporary messages across our sky, telling the story of magnetic field lines reconnecting in the sun's corona and charged particles streaming across interplanetary space to paint our atmosphere with light. The next time you experience a disruption in your GPS navigation, or notice flickering in your electrical power, you might pause to consider whether our sun has sent another message across the void. In our interconnected technological world, we have become increasingly sensitive to our star's electromagnetic whispers, creating an unintended but intimate connection between solar physics and daily life. The sun's influence reminds us that despite our technological sophistication, we remain creatures of a particular star in a particular place at a particular time in cosmic history. We have evolved within the embrace of our star's magnetic field, adapted to its rhythms and cycles, and built our civilization in the spaces between its storms. Understanding solar flares and their effects on our world is not just an academic exercise, but a recognition of our ongoing relationship with the cosmic forces that continue to shape our planet and our lives. In this gentle recognition of our place within the sun's domain, we find both humility and wonder. The sun's magnetic choreography reaches its crescendo in what we call solar maximum, that remarkable peak in our star's 11-year cycle when its magnetic personality becomes most dramatically expressive. Picture the sun during these times as a restless sleeper, tossing and turning with magnetic energy that simply cannot contain itself within the orderly confines of its usual behavior. During solar maximum, the sun's magnetic field lines become increasingly tangled and complex, like headphone wires left too long in a pocket. These field lines stretch and twist until they reach a breaking point, snapping back into simpler configurations with explosive force. It's during these magnetic restructuring events that we witness the sun's most spectacular displays of power, the solar flares that can influence our world in ways both subtle and profound. The sunspot cycle, which we've touched upon before, becomes particularly pronounced during these peak years. These dark patches on the sun's surface multiply and cluster, sometimes growing to sizes that dwarf our entire planet. Each sunspot is a window into the sun's magnetic soul, a place where field lines have become so concentrated and twisted that they actually suppress the normal convection of hot plasma, creating cooler regions that appear dark against the brilliant solar surface. But it's not just the number of sunspots that increases during solar maximum. The sun's corona, that ethereal atmosphere visible during total solar eclipses, becomes dramatically more active and structured. Magnetic field lines loop and arch through the corona like invisible highways, guiding the flow of charged particles in graceful trajectories that can extend millions of kilometers into space. When these coronal loops become unstable, they can release enormous amounts of energy in the form of solar flares and coronal mass ejections. The process begins deep within the sun's interior, in the convection zone where hot plasma churns and roils like a cosmic cauldron. This constant motion of electrically charged material generates powerful magnetic fields through a process called the dynamo effect. Imagine stirring a pot of metallic soup with a magnetic spoon, and you begin to understand how the sun's rotation and convection work together to create and amplify magnetic fields. These magnetic fields, once generated, don't simply stay put. They're carried upward by the convecting plasma, emerging at the sun's surface like invisible weeds pushing through soil. As they break through the photosphere, they create the complex magnetic landscape that gives rise to sunspots, solar flares, and all the other phenomena we associate with solar activity. The mathematics of this process is elegantly complex. The sun's magnetic field lines follow precise physical laws, bending and twisting according to the principles of magnetohydrodynamics. When field lines of opposite polarity are brought together, they can undergo a process called magnetic reconnection, suddenly snapping into new configurations and releasing tremendous amounts of stored magnetic energy in the process. This energy release is what creates a solar flare. In a matter of minutes, a region of the sun's surface can brighten dramatically, releasing as much energy as billions of hydrogen bombs. The energy manifests across the entire electromagnetic spectrum, from radio waves to gamma rays, creating a beacon of activity that can be detected by our instruments here on Earth. The charged particles accelerated during these flares don't simply disappear. they stream outward from the sun at incredible speeds, following the magnetic field lines like cars on a cosmic highway. Some of these particles are trapped in the sun's magnetic field, bouncing back and forth between the sun's north and south poles in a process that can last for hours or even days. Meanwhile, the sun's rotation adds another layer of complexity to this magnetic symphony. As the sun spins, it winds up its magnetic field lines like a cosmic dynamo, creating the twisted, rope-like structures we observe extending far into the solar system. These structures, called flux ropes, can become unstable and erupt as coronal mass ejections, sending billions of tons of magnetized plasma racing through space at speeds of several million kilometers per hour. The 11-year cycle itself is a manifestation of the sun's magnetic memory. Deep within the sun's interior, the magnetic field gradually builds up strength and complexity until it reaches a point of maximum instability. Then, like a rubber band stretched to its breaking point, the field suddenly reorganizes itself, flipping its polarity and beginning the cycle anew. This magnetic reversal is not instantaneous, but unfolds over several years, creating the gradual transition from solar maximum to solar minimum. During this transition, the sun's activity slowly decreases, sunspots become fewer and smaller, and the frequency of solar flares diminishes. The sun settles into a more quiescent state, its magnetic field lines becoming more ordered and stable. But even during solar minimum, the sun is not truly quiet. Coronal holes, regions where the sun's magnetic field lines extend far into space rather than looping back to the surface, continue to emit high-speed streams of charged particles. These solar wind streams, while less dramatic than the explosive events of solar maximum, provide a steady background of particles that interact with Earth's magnetosphere and contribute to the ongoing dance between our planet and our star. The sun's magnetic cycle also influences the structure of the entire solar system. The solar wind carries the sun's magnetic field outward, creating what we call the interplanetary magnetic field. This field extends far beyond the orbit of Pluto, creating a vast magnetic bubble called the heliosphere that partially shields our solar system from cosmic rays originating in deep space. During periods of high solar activity, this magnetic shield becomes stronger and more turbulent, providing better protection from cosmic rays, but also creating more opportunities for dramatic space weather events. During solar minimum, the shield weakens, allowing more cosmic rays to penetrate the inner solar system, but reducing the likelihood of severe geomagnetic storms. The complexity of these magnetic interactions continues to surprise scientists. Recent observations have revealed that the sun's magnetic field has a memory that extends far beyond the 11-year cycle. Subtle patterns in solar activity suggest that the sun remembers its magnetic history over multiple cycles, creating longer-term variations that can influence Earth's climate over decades or even centuries. These longer cycles, with periods of roughly 88 years or longer, may be responsible for historical climate variations such as the Little Ice Age of the 17th century, when solar activity was unusually low for an extended period. During this time, known as the Maunder Minimum, sunspots were rarely observed, and Earth experienced cooler temperatures, particularly in Europe and North America. The sun's magnetic influence extends even to the formation of clouds in Earth's atmosphere. Cosmic rays, those high-energy particles from deep space, can trigger the formation of cloud condensation nuclei when they collide with molecules in our atmosphere. When solar activity is high, the enhanced magnetic field reduces the number of cosmic rays reaching Earth, potentially affecting cloud formation and, consequently, climate. This connection between solar magnetism and terrestrial weather patterns represents one of the most subtle, yet potentially significant ways that our star influences our world. While the direct warming effect of solar radiation variations is relatively small, the indirect effects through cosmic ray modulation and atmospheric chemistry may be more substantial than previously thought. As we continue to study the Sun's magnetic behavior, we're discovering that its influence on Earth operates through multiple pathways, each with its own timescales and mechanisms. From the immediate effects of solar flares on our technological systems to the long-term climate influences of solar cycles, the Sun's magnetic personality shapes our world in ways both obvious and hidden. The story of solar magnetism is ultimately a story of connection and influence, of how the internal dynamics of our star reach across the vast emptiness of space to touch our daily lives. In the gentle fluctuations of Earth's magnetic field, in the dancing curtains of the aurora, in the subtle variations of our climate, we can read the signatures of the Sun's magnetic heartbeat, a rhythm that has been pulsing for billions of years and will continue long after we're gone. As you drift towards sleep tonight, perhaps you can sense something of this cosmic connection, this invisible thread that links you to the roiling magnetic cauldron of our nearest star. The Sun's magnetic field doesn't simply end at its visible surface. Instead, it extends outward through the solar system in what astronomers call the heliosphere, a vast bubble of solar influence that encompasses all the planets and reaches far beyond Pluto's orbit. This magnetic cocoon shapes the very environment in which Earth exists, creating a dynamic relationship between our star and our world that operates on multiple timescales. Within this heliosphere, the solar wind carries with it the Sun's magnetic field lines, twisted and stretched by the star's rotation into a complex spiral pattern known as the Parker spiral. Named after physicist Eugene Parker, who first predicted its existence, this spiral structure means that the magnetic field lines connecting the Sun to Earth are not straight but curved, following the rotation of our star as it spins once every 27 days. The strength and orientation of these magnetic field lines fluctuate constantly, creating what space physicists call space weather. Just as terrestrial weather affects our daily lives through temperature, precipitation, and wind patterns, space weather influences the technological systems we've become increasingly dependent upon. When the Sun's magnetic field undergoes rapid changes, particularly during solar flares and coronal mass ejections, the effects ripple outward through the heliosphere like waves on a cosmic pond. These magnetic disturbances interact with Earth's own magnetic field in ways that can be both beautiful and disruptive. The aurora borealis and aurora australis, those ethereal curtains of light that dance across polar skies, are direct manifestations of solar magnetic activity colliding with our planet's protective magnetic shield. As charged particles from the Sun spiral down Earth's magnetic field lines toward the poles, they collide with atoms in our upper atmosphere, exciting them to emit light in characteristic colors. Oxygen produces the familiar green glow, while nitrogen contributes blues and purples to the celestial display. But the Sun's magnetic influence extends far beyond creating pretty lights in the sky. The same magnetic storms that produce spectacular auroras can wreak havoc on our technological infrastructure. Power grids, designed for terrestrial electrical loads, can be overwhelmed by the induced currents that result from rapidly changing magnetic fields. The famous Quebec blackout of 1989 serves as a stark reminder of our vulnerability to solar magnetic activity. A coronal mass ejection struck Earth's magnetosphere, inducing currents in the power grid that caused transformers to fail, plunging millions into darkness for up to 9 hours. Satellites, those silent sentinels that enable everything from GPS navigation to global communications, are particularly vulnerable to solar magnetic storms. Operating beyond the protective embrace of Earth's atmosphere, they face the full fury of solar particle bombardment during magnetic disturbances. The energetic particles can damage sensitive electronics, disrupt solar panels, and even alter orbital trajectories through atmospheric heating that increases drag on low Earth orbit satellites. The The sun's magnetic field also acts as a shield of sorts, deflecting cosmic rays that would otherwise bombard the inner solar system. These cosmic rays, high-energy particles originating from distant supernovae and other exotic cosmic phenomena, are partially blocked by the heliosphere's magnetic boundary. During periods of reduced solar activity, when the sun's magnetic field weakens, more cosmic rays can penetrate the inner solar system, potentially affecting Earth's climate and atmospheric chemistry. This cosmic ray connection hints at one of the most intriguing aspects of solar magnetic variability: its potential influence on Earth's long-term climate patterns. While the sun's total energy output varies by only about 0.1% during the solar cycle, the magnetic field's modulation of cosmic rays may amplify these small changes through complex atmospheric processes. Some researchers propose that cosmic rays help seed cloud formation in Earth's atmosphere, meaning that solar magnetic activity could indirectly influence global cloud cover and, consequently, climate. The relationship between solar magnetic activity and terrestrial climate becomes particularly fascinating when viewed over longer timescales. Historical records suggest that periods of unusually low solar activity, characterized by few sunspots and weak magnetic fields, coincide with cooler global temperatures. The Maunder minimum, a period from roughly 1645 to 1715 when sunspots virtually disappeared, corresponded with the depths of the Little Ice Age in Europe and North America. While the exact mechanisms remain debated, the correlation suggests that the sun's magnetic behavior may influence Earth's climate on timescales of decades to centuries. Modern satellite observations have revealed the sun's magnetic field to be even more complex and dynamic than previously imagined. The solar wind, that constant stream of charged particles flowing outward from the sun, carries with it a detailed record of magnetic activity in the solar corona. By studying these magnetic signatures as they pass Earth, scientists can reconstruct the three-dimensional structure of the sun's magnetic field and track how it evolves over time. The heliosphere itself undergoes long-term changes as the solar system moves through the galaxy. Our star system currently resides within a region of space called the local interstellar cloud, a relatively warm and thin collection of gas and dust. The boundary between the heliosphere and this interstellar medium, known as the heliopause, represents the limit of the sun's magnetic influence. The Voyager spacecraft, humanity's most distant ambassadors, have crossed this boundary and begun sampling the true interstellar environment beyond our star's reach. As we continue to study the sun's magnetic field and its far-reaching effects, we're discovering that our relationship with our star is far more intimate and complex than simple heating and lighting. The magnetic threads that connect the sun to Earth carry with them the potential for both creation and disruption, beauty and chaos. They remind us that we are not isolated inhabitants of a small world, but participants in a vast, interconnected system of magnetic forces that spans the solar system. The sun's magnetic field, in its endless dance of formation and destruction, connection and separation, continues to shape our world in ways both subtle and profound. It influences the very air we breathe, the technology we depend upon, and perhaps even the long-term stability of our climate. As we drift towards sleep, we can take comfort in knowing that this ancient magnetic embrace has cradled our world for billions of years, creating the conditions that allowed life to flourish, while occasionally reminding us of the dynamic, ever-changing nature of our cosmic home. Looking at our cosmic journey so far, we've traced gravity's gentle influence from the primordial universe through the birth of galaxies and the intricate choreography of planetary systems. Now, as we drift deeper into this celestial narrative, we turn our attention to something both more intimate and more mysterious: the sun itself, and the extraordinary magnetic forces that dance within its glowing heart. You see, while gravity provides the grand architecture of our cosmic neighborhood, holding planets in their orbits and stars in their galaxies, the Sun harbors another kind of force altogether. Deep within its churning plasma, magnetic fields twist and writhe in patterns so complex they would make the most elaborate Celtic knot seem simple by comparison. These invisible lines of force, stronger than any magnet you've ever encountered, shape the very character of our nearest star, and, in turn, influence every aspect of life on Earth. Picture, if you will, the Sun not as the serene golden orb we see during the day, but as a roiling magnetic dynamo. Beneath its photosphere, that brilliant surface that warms our faces, lies a realm of perpetual motion where charged particles spiral along magnetic highways at temperatures exceeding 10 million degrees. Here, in this plasma laboratory, more extreme than anything we could ever create on Earth, magnetic forces reign supreme. The Sun's magnetic field emerges from a process so elegant it almost seems choreographed. Deep in the solar interior, electrically charged particles flow in vast currents, driven by the star's rotation and the convective motion of its outer layers. Just as a bicycle dynamo generates electricity through motion, these flowing charges create magnetic fields that thread through the solar plasma like invisible ribbons of force. But unlike the steady, predictable field of a bar magnet, the Sun's magnetism is dynamic, ever-changing, following an intricate cycle that takes approximately 11 years to complete. During this solar cycle, the Sun's magnetic personality transforms entirely. At solar minimum, the magnetic field is relatively simple and organized, with clear north and south poles, much like Earth's field. But as the cycle progresses towards solar maximum, something remarkable happens. The Sun's differential rotation begins to stretch and twist the magnetic field lines. You see, the Sun doesn't rotate as a solid body. Its equator spins faster than its poles, completing a rotation in about 25 days, while the polar regions take more than 30 days to make the same journey. This differential rotation acts like a cosmic taffy puller, stretching the magnetic field lines until they become increasingly tangled and complex. As these magnetic field lines twist and wrap around the Sun, they store enormous amounts of energy, like rubber bands being wound tighter and tighter. Eventually, something has to give. The field lines become so stressed that they snap and reconnect in violent events called magnetic reconnection. When this happens, the stored magnetic energy is released in spectacular fashion, creating the phenomena we observe as solar flares and coronal mass ejections. Solar flares are among the most powerful explosions in our solar system, releasing energy equivalent to billions of nuclear bombs in a matter of minutes. These eruptions occur when twisted magnetic field lines suddenly snap back to a more relaxed configuration, accelerating particles to incredible speeds and heating the solar corona to temperatures of hundreds of millions of degrees. The energy released in a single large flare could power human civilization for thousands of years. But perhaps even more dramatic are coronal mass ejections, or CMEs, where the Sun literally hurls billions of tons of its own plasma into space at speeds exceeding 1,000,000 miles per hour. These magnetic storms begin when field lines become so tangled that they form what solar physicists call magnetic flux ropes, twisted structures that can no longer be contained by the Sun's gravity. When these flux ropes erupt, they carry with them a piece of the Sun's magnetic field, creating a magnetic cloud that races through the solar system. The dance of these magnetic forces creates the Sun's most visible features. Sunspots, those dark patches that appear on the solar surface, are regions where intense magnetic fields have pushed up through the photosphere. The magnetic field in these regions is so strong that it suppresses the normal convection of hot plasma, creating areas that are cooler and therefore darker than their surroundings. These magnetic anchors can be larger than Earth itself, persisting for weeks or even months as they rotate with the sun. The number and distribution of sunspots follow the 11-year solar cycle, serving as visible markers of the sun's changing magnetic mood. At solar minimum, the sun's face may be completely spotless for days or weeks at a time, but as the cycle builds toward maximum, sunspot groups bloom across the solar surface like magnetic flowers, appearing first at high latitudes and gradually migrating toward the equator as the cycle progresses. Above the sunspots, the sun's atmosphere erupts in magnificent arches and loops of glowing plasma. These solar prominences and filaments trace out the invisible magnetic field lines, revealing the three-dimensional structure of the sun's magnetic architecture. Some of these structures are relatively stable, persisting for weeks as plasma flows along magnetic highways high above the solar surface. Others are more dynamic, twisting and evolving as the underlying magnetic field changes. The sun's magnetic field extends far beyond its visible surface, creating what we call the heliosphere, a vast magnetic bubble that encompasses our entire solar system. This interplanetary magnetic field, carried outward by the solar wind, influences the space environment around all the planets. It deflects cosmic rays from interstellar space, modulates the formation of cometary tails, and creates the complex magnetic interactions we observe throughout the solar system. Here on Earth, we feel the effects of the sun's magnetic activity in profound ways. When solar flares and coronal mass ejections arrive at our planet, they interact with Earth's own magnetic field, creating the beautiful auroras that dance across polar skies. But these same magnetic storms can also disrupt our technology, affecting satellite communications, GPS systems, and even power grids on the ground. The sun's magnetic cycle also influences Earth's climate in subtle but important ways. During periods of high solar activity, the sun's increased magnetic field more effectively shields our planet from galactic cosmic rays. This cosmic ray modulation may affect cloud formation in Earth's atmosphere, potentially influencing global temperature patterns over the course of the solar cycle. As we continue our gentle journey through the cosmos, remember that the sun's magnetic dance is not just a distant spectacle, but an intimate part of our daily existence. The magnetic forces that twist and turn in the solar interior help regulate the flow of energy that warms our world, drives our weather, and makes life possible. Every sunrise brings with it the continuing story of magnetic forces in constant motion, a stellar heartbeat that has been pulsing for over 4.5 billion years. Tonight, as you drift towards sleep, imagine the sun on the other side of our world, its magnetic field lines stretching and twisting in their eternal dance. Even in darkness, that stellar dynamo continues its work, preparing for tomorrow's dawn when its light will once again grace our sky. In the gentle rhythm of the solar magnetic cycle, we find another kind of cosmic music, a magnetic symphony that plays out across years and decades, connecting our small world to the grand magnetic architecture of our star. The sun's magnetic story is far from over. As we develop new technologies to observe and understand our nearest star, we continue to discover new aspects of its magnetic personality. Space-based observatories peer into the sun's corona with unprecedented detail, while computer models help us understand the complex physics of magnetic reconnection and plasma dynamics. Each new discovery adds another verse to the magnetic poem that our star has been writing in the sky for billions of years. So rest now, knowing that you are held not only by Earth's gravity, but also embraced by the vast magnetic influence of our sun, a star whose magnetic heartbeat helps orchestrate the cosmic dance that makes our existence possible. The dance between our sun and Earth extends far beyond the visible aurora that paint our polar skies. Deep within our planet's core, currents of molten iron swirl in patterns that mirror, in their own way, the magnetic choreography unfolding 93 million miles away. These terrestrial currents generate Earth's magnetic field, our protective shield that has safeguarded life for billions of years. Yet this shield itself responds to the sun's magnetic moods with a sensitivity that speaks to the profound interconnectedness of our cosmic neighborhood. When solar wind carries the sun's magnetic field lines toward Earth, something remarkable occurs at the boundary where these two magnetic domains meet. The magnetopause, that invisible frontier surrounding our planet, becomes a membrane of interaction where solar and terrestrial magnetism engage in their ancient dialogue. Solar particles, guided by magnetic field lines, find pathways through this boundary, particularly at the polar regions where Earth's magnetic field lines converge and dive deep into our planet's interior. This interaction creates what scientists call the magnetosphere, a vast magnetic bubble that extends far beyond our atmosphere into space. Within this bubble, charged particles from the sun become trapped, creating radiation belts that circle our planet like invisible donuts of energy. These Van Allen belts, discovered in the early days of space exploration, wax and wane with solar activity, swelling during periods of high solar magnetic activity and contracting during solar minimum. The effects of this magnetic coupling extend into the very chemistry of our upper atmosphere. When energetic solar particles cascade down magnetic field lines into Earth's polar regions, they collide with atmospheric molecules, breaking apart nitrogen and oxygen in ways that create nitric oxide and other compounds. These chemical changes, triggered by solar magnetic activity, can persist for months or even years, slowly altering the composition of our stratosphere and influencing the delicate balance of gases that regulate our climate. Consider how this magnetic connection operates across multiple timescales simultaneously. On the shortest scale, individual solar flares can trigger geomagnetic storms within hours, causing compass needles to waver and disrupting radio communications. On intermediate scales, the sun's 27-day rotation period creates recurring patterns in solar wind and magnetic field strength that Earth's magnetosphere learns to anticipate and respond to. And on the longest scales, the 11-year solar cycle drives profound changes in the intensity and character of solar magnetic activity that leaves its signature in everything from tree rings to ice cores to the very chemistry of our atmosphere. The magnetic field lines that connect Sun and Earth are not merely abstract concepts, but physical realities that channel energy and information across the vast emptiness of space. Solar wind particles spiral along these invisible highways, carrying with them the magnetic memory of conditions in the sun's corona. When these particles reach Earth, they bring news of solar storms that erupted days earlier, creating a kind of magnetic telegraph system that has operated since the formation of our solar system. This magnetic communication system becomes particularly evident during periods of high solar activity, when coronal mass ejections launch billions of tons of magnetized plasma toward Earth. These magnetic clouds, as they're sometimes called, carry within them the twisted and compressed magnetic fields of the sun's corona. When they encounter Earth's magnetosphere, the interaction can be gentle or violent, depending on the relative orientation of the magnetic fields involved. If the magnetic field within a coronal mass ejection points in the same direction as Earth's magnetic field, the interaction is relatively benign, like two magnets placed side by side with their poles aligned. But if the magnetic fields are oppositely oriented, a process called magnetic reconnection occurs, where field lines break and rejoin in explosive fashion, transferring enormous amounts of energy into Earth's magnetosphere within minutes. This energy transfer manifests in ways both beautiful and potentially disruptive. The same magnetic reconnection that creates the most spectacular auroral displays can also induce powerful electric currents in Earth's upper atmosphere and on its surface. These currents, following the paths of least resistance, can flow through power lines, pipelines, and even railroad tracks, sometimes with enough intensity to trip circuit breakers or accelerate corrosion in metal infrastructure. The magnetic connection between Sun and Earth also influences the behavior of cosmic rays, those high-energy particles that constantly bombard our solar system from distant stars and galaxies. The Sun's magnetic field, carried throughout the solar system by the solar wind, acts as a partial shield against these cosmic rays. During periods of high solar magnetic activity, this shielding effect increases, reducing the flux of cosmic rays reaching Earth. Conversely, during solar minimum, when the Sun's magnetic field is weaker and less organized, more cosmic rays penetrate the inner solar system. These variations in cosmic ray intensity may have subtle but significant effects on Earth's climate system. Cosmic rays can influence cloud formation by creating ions in the atmosphere that serve as condensation nuclei for water droplets. Changes in cosmic ray flux, driven by solar magnetic variability, might therefore affect global cloud cover, and consequently, the amount of solar energy reflected back to space versus absorbed by Earth's surface. The magnetic relationship between Sun and Earth extends even to the microscopic level, influencing the behavior of particles in our planet's radiation belts. During geomagnetic storms, these trapped particles can be accelerated to tremendous energies, creating what space physicists call killer electrons that pose hazards to satellites and astronauts. The acceleration mechanism depends on the complex interaction between solar wind magnetic fields and Earth's magnetosphere, demonstrating how magnetic phenomena at the Sun can have direct consequences for human technology and safety in space. Recent discoveries have revealed that Earth's magnetic field exhibits its own form of space weather, with magnetic storms that can persist for days or weeks after the initial solar disturbance has passed. These extended periods of magnetic unrest occur when the Sun's magnetic field becomes temporarily connected to Earth's magnetic field, creating a more direct pathway for energy transfer. During such periods, the magnetosphere rings like a bell struck by the solar wind, with oscillations that can be detected by sensitive magnetometers on the ground. The study of these magnetic connections has also revealed the dynamic nature of Earth's magnetosphere, which breathes and pulses in response to solar wind pressure and magnetic field variations. When solar wind pressure increases, the magnetosphere compresses, bringing potentially hazardous radiation closer to Earth's surface. When pressure decreases, the magnetosphere expands, providing greater protection, but also creating conditions for different types of magnetic disturbances. As we drift deeper into understanding these magnetic relationships, we begin to appreciate how the Sun's magnetic field acts as both sculptor and conductor of conditions throughout the solar system. The heliospheric magnetic field, as it's known, extends far beyond the orbit of Pluto, creating a vast magnetic environment within which all solar system bodies exist. This magnetic environment is not static, but constantly evolving, shaped by the Sun's rotation, the solar cycle, and the complex dynamics of solar wind interactions with planetary magnetic fields and atmospheres. In this grand magnetic symphony, Earth plays the role of both receiver and responder, its magnetic field serving as an antenna that captures and translates solar magnetic signals into terrestrial phenomena. The northern and southern lights become visible manifestations of invisible magnetic processes, the aurora serving as Earth's way of making the magnetic connection with our star apparent to human eyes. These lights, dancing across polar skies in patterns that mirror the magnetic field configurations far above, remind us that we live within a vast magnetic system that connects our world to the cosmic forces that shaped it and continue to influence its evolution. The magnetic thread that binds Sun and Earth speaks to a deeper truth about our place in the cosmos. We are not isolated on our small planet, but intimately connected to our star through invisible fields of force that carry energy, information, and influence across the void. We've explored the cosmic dance of gravity, from the birth of the first stars to the grand architecture of the cosmic web. We've witnessed how dark matter weaves invisible threads through space, binding galaxies in their eternal waltz, and seen how planets learn their steps in the gravitational ballet that began billions of years ago. Now, as our journey through the cosmos draws toward its gentle close, we turn to perhaps the most intimate chapter in this story of cosmic forces. How the sun itself dances with our world through the invisible threads of magnetism. The sun, that familiar golden disk that rises each morning and sets each evening, is far from the steady, unchanging beacon it appears to be. Beneath its brilliant surface lies a churning dynamo of magnetic forces, a stellar engine that breathes and pulses with rhythms that span years, decades, and centuries. These magnetic heartbeats reach across the 93 million miles of space that separate us from our star, touching our planet with invisible fingers that shape everything from the aurora dancing across polar skies to the very climate patterns that have guided the evolution of life on Earth. Just as gravity conducted the grand symphony we've been following, magnetism composes its own quieter but no less profound music, where gravity works through the patient accumulation of mass and the gentle curvature of space-time. Magnetism flows through the complex choreography of charged particles, electric currents, and magnetic fields that permeate the solar system like an invisible web of influence. To understand this magnetic dance, we must first peer into the sun's hidden depths, where temperatures soar to millions of degrees, and matter exists in a state so exotic that atoms themselves are torn apart into their constituent pieces. Here, in the sun's convective zone, vast rivers of plasma rise and fall in patterns that dwarf any earthly weather system. These plasma currents, carrying with them the fundamental building blocks of matter, create the magnetic fields that will eventually emerge at the sun's surface and ripple outward through the solar system. The sun's magnetic field is not a simple, uniform structure like the field around a child's bar magnet. Instead, it's a complex, ever-changing tapestry woven from countless individual magnetic loops and filaments. Some of these magnetic structures are small and ephemeral, lasting only hours or days. Others are vast and persistent, maintaining their basic form for months or even years as they slowly evolve and migrate across the solar surface. As these magnetic field lines emerge from the sun's interior and pierce through its visible surface, they create the dark patches we call sunspots. These are not truly dark, of course. They shine with the brightness of an electric arc, but they appear dark only in contrast to the even more brilliant surrounding solar surface. Each sunspot is a window into the sun's magnetic soul, a place where field lines have become so concentrated and twisted that they suppress the normal convection that brings heat from the solar interior to the surface. The sun's magnetic activity follows a rhythm as regular as a cosmic heartbeat, waxing and waning over an 11-year cycle that has been faithfully recorded by astronomers for centuries. During solar maximum, the sun's surface becomes a riot of magnetic activity, covered with numerous sunspot groups, solar flares, and coronal mass ejections. The magnetic field lines become increasingly tangled and stressed, like rubber bands stretched to their breaking point, until finally they snap and reconnect in violent releases of energy that can outshine entire stars for brief moments. But this is not chaos, despite its apparent violence. The sun's magnetic cycle represents a profound example of self-organization in nature, a complex system that maintains its overall structure while constantly changing its details. As the magnetic field lines twist and tangle during the active phase of the solar cycle, they gradually work their way toward the poles, where they cancel out the existing polar magnetic field and eventually reverse it entirely. This magnetic pole reversal happens every 11 years, meaning that the Sun's complete magnetic cycle actually takes 22 years to return to its original configuration. During solar minimum, when sunspot activity drops to its lowest levels, the Sun might appear to be magnetically quiet, but this apparent calm is deceptive. Even at its most peaceful, our star maintains a complex magnetic architecture that extends far beyond its visible surface. The Sun's magnetic field doesn't simply end at the solar atmosphere, but continues outward, carried by the solar wind, that constant stream of charged particles that flows from the Sun in all directions at speeds of hundreds of kilometers per second. This solar wind is itself a magnetic phenomenon, a plasma that carries embedded within it the twisted remnants of the Sun's magnetic field. As this magnetized plasma expands into space, it creates what scientists call the interplanetary magnetic field, a vast structure that fills the entire solar system with the Sun's magnetic influence. The field lines spiral outward like the arms of a cosmic whirlpool, shaped by the Sun's rotation into elegant curves that extend past the orbits of all the planets. When this solar wind encounters Earth, it doesn't simply bounce off our planet's surface like a gentle breeze. Instead, it interacts with Earth's own magnetic field in a complex dance of attraction and repulsion, compression and expansion. Our planet, you see, is itself a magnet, with its own magnetic field generated deep within its molten iron core by the same kind of dynamo processes that create the Sun's magnetic field, though on a much smaller scale. The collision between the solar wind and Earth's magnetosphere creates one of the most beautiful and dynamic structures in our immediate cosmic neighborhood. The magnetosphere, that vast invisible bubble of magnetic influence that surrounds our planet, is constantly being sculpted and reshaped by the pressure of the solar wind. On the side facing the Sun, the magnetosphere is compressed to within about 10 Earth radii of our planet's surface. On the night side, it's stretched into a long, comet-like tail that extends far beyond the Moon's orbit. Within this magnetospheric boundary, charged particles from the solar wind become trapped, bouncing back and forth along magnetic field lines in the radiation belts that encircle our planet. These trapped particles create a dynamic, ever-changing population of energetic electrons and protons that pose challenges for spacecraft and astronauts, but also contribute to some of the most spectacular displays in nature. The aurora, those shimmering curtains of light that dance across the polar skies, are perhaps the most visible manifestation of the Sun's magnetic connection to Earth. When the Sun releases a particularly strong burst of magnetic energy in the form of a coronal mass ejection, billions of tons of magnetized plasma race across interplanetary space at speeds that can exceed 1,000 kilometers per second. When this plasma cloud encounters Earth's magnetosphere, it can trigger a geomagnetic storm that sends cascades of energetic particles down into our planet's upper atmosphere. These particles, guided by Earth's magnetic field lines toward the polar regions, collide with atoms and molecules in the thin air 60 to 400 kilometers above the surface. The collisions excite these atmospheric atoms, causing them to emit light in the characteristic colors of the aurora, the green glow of oxygen at lower altitudes, the red shimmer of oxygen at higher elevations, and the blue and purple hues of nitrogen. The result is a light show of such ethereal beauty that it has inspired myths and legends in every culture that has witnessed it. But the Sun's magnetic influence on Earth extends far beyond these spectacular displays. The same geomagnetic storms that create enhanced aurora can also disrupt our increasingly electronic civilization. Strong magnetic disturbances can induce electrical currents in power lines, potentially causing blackouts that affect millions of people. They can interfere with radio communications, disrupt GPS signals, and pose radiation hazards to astronauts and airline passengers flying polar routes. The Sun's magnetic cycle also appears to influence Earth's climate in subtle but measurable ways. During periods of high solar activity, the increased solar wind and magnetic field strength can partially shield Earth from galactic cosmic rays, high-energy particles that stream in from interstellar space. These cosmic rays are thought to play a role in cloud formation, so changes in their intensity could affect global cloud cover and, consequently, Earth's temperature. The relationship is complex and still being studied, but it represents yet another way in which the Sun's magnetic heartbeat resonates through our planet's systems. Looking deeper into the past, scientists have found evidence that variations in solar magnetic activity may have influenced major climate events throughout Earth's history. The Maunder Minimum, a period from roughly 1645 to 1715, when sunspot activity was unusually low, coincided with some of the coldest temperatures of the Little Ice Age in Europe and North America. While solar variability alone cannot explain all climate changes, it appears to be one important factor in the complex symphony of influences that shape our planet's long-term climate patterns. The magnetic connection between Sun and Earth is not merely a one-way relationship. Earth's magnetosphere doesn't simply receive the Sun's magnetic influence passively, but actively participates in the interaction. The boundary between the solar wind and Earth's magnetic field, called the magnetopause, is a dynamic interface where magnetic field lines from both sources can connect and reconnect in processes that transfer energy and particles between the two systems. This magnetic reconnection is one of the most fundamental processes in plasma physics, occurring wherever magnetic fields of different orientations come into contact. When field lines from the Sun and Earth connect, they can suddenly snap and rearrange themselves, releasing energy that accelerates particles to high speeds and drives the complex dynamics of the magnetosphere. It's a process that occurs on scales from the microscopic to the planetary, playing out in laboratory experiments, in Earth's magnetosphere, in the Sun's atmosphere, and in the space between stars. The Sun's magnetic influence extends to all the planets in our solar system, each responding according to its own magnetic characteristics. Jupiter, with its powerful magnetic field generated by convection in its metallic hydrogen interior, traps solar wind particles in radiation belts far more intense than Earth's. The interaction between Jupiter's magnetic field and the solar wind creates radio emissions so strong they can be detected by amateur radio operators on Earth. Mars, having lost most of its global magnetic field billions of years ago, offers little resistance to the solar wind, which gradually strips away the planet's thin atmosphere particle by particle. Venus, despite having no intrinsic magnetic field, generates a weak magnetosphere through the interaction between the solar wind and its dense atmosphere. Even distant Pluto, at the very edge of the solar system, feels the Sun's magnetic touch through the tenuous solar wind that reaches even those remote regions. The dance between solar and planetary magnetism is not static, but evolves over time as the Sun itself changes. Our star is a middle-aged star, about halfway through its 10 billion-year main sequence lifetime. As it ages, subtle changes in its internal structure will gradually alter its magnetic behavior. Billions of years in the future, as the Sun begins to exhaust its nuclear fuel and expand into a red giant, its magnetic field will likely become more chaotic and variable, with consequences for the entire solar system that we can only begin to imagine. But these changes lie in the distant future. For now, we live in an era when the Sun's magnetic cycle provides a relatively stable, predictable rhythm that has persisted for billions of years. This stability has been crucial for the development of life on Earth, providing a magnetic environment that protects our planet's atmosphere while allowing enough energetic particles through to drive the chemical processes that may have helped spark life's beginning. The magnetic relationship between Sun and Earth is ultimately a story of connection across vast distances, of invisible forces that bind our world to its star in ways that complement and enhance the gravitational dance we explored earlier. Where gravity provides the stable, predictable framework that keeps planets in their orbits, magnetism adds the dynamic, ever-changing interactions that make each world's environment unique. As you settle deeper into rest tonight, perhaps you can sense something of this magnetic embrace that surrounds you. The Earth's magnetic field, generated by the churning motions of molten iron hundreds of kilometers beneath your feet, extends upward through your body and outward into space, connecting you to the Sun's own magnetic field through the invisible threads of the solar wind. You are part of this magnetic system, protected by it, influenced by it, and connected through it to the nearest star. The Sun's magnetic heartbeat, pulsing with its 11-year rhythm, has been keeping time for our planet since long before life began. It will continue its steady pulse long after our current civilization has passed into history, providing the magnetic backdrop against which countless future generations of life will evolve and flourish. And so we reach the gentle conclusion of our cosmic journey through the intricate dance between our star and our world. We've traveled from the Sun's turbulent magnetic heart to Earth's protective magnetosphere, witnessing how these invisible forces shape everything from the shimmering auroras that paint our polar skies to the delicate technological networks that connect our modern lives. The story we've explored tonight is ultimately one of profound interconnectedness. The same magnetic field lines that twist and tangle in the Sun's corona reach across 93 million miles of space to caress our planet's protective shield. The charged particles that spiral through the solar wind carry with them the memory of nuclear furnaces burning in our star's core, delivering energy that once powered the very atoms in your body during their stellar birth billions of years ago. This cosmic relationship between the Sun and Earth represents something far more beautiful than mere physics equations or electromagnetic phenomena. It reveals the elegant choreography that governs our universe, where seemingly chaotic events like solar flares emerge from the patient, methodical processes of magnetic reconnection, where explosive releases of energy follow mathematical laws as precise as clockwork, and where our planet's response to stellar tantrums demonstrates the remarkable resilience of the systems that shelter life. The magnetosphere that surrounds our world isn't simply a barrier against the solar wind. It's a dynamic, breathing boundary that expands and contracts with each solar cycle, that channels cosmic particles into spectacular light shows, and that has been faithfully protecting our atmosphere for billions of years. Without this magnetic embrace, our world would likely have suffered the same fate as Mars, slowly losing its atmosphere to space until only a thin, cold shell remained, where once thick air supported flowing water and perhaps even life. Tonight, as you drift towards sleep, solar particles are streaming past our planet at speeds that would carry them from New York to Los Angeles in less than a minute. Some of these particles, guided by Earth's magnetic field, are spiraling down toward the polar regions where they collide with oxygen and nitrogen molecules hundreds of miles above the surface, creating curtains of green and red light that dance silently in the Arctic darkness. Indigenous peoples of the far north have watched these same lights for thousands of years, weaving stories of spirits and ancestors into the aurora's shifting patterns, unknowingly celebrating the same magnetic processes we've explored together. The Sun's magnetic heartbeat, with its 11-year rhythm of quiet and activity, will continue long after our civilization has transformed into something we cannot imagine. Solar maximum will follow solar minimum in an ancient pattern that began when our star first ignited and will persist until its nuclear fuel is finally exhausted billions of years from now. During quiet periods, space weather becomes gentle and predictable, allowing our satellites to orbit peacefully and our power grids to hum with steady efficiency. But when the sun awakens from its magnetic slumber, when sunspot numbers climb and coronal mass ejections thunder across interplanetary space, we are reminded of our star's tremendous power and our planet's remarkable ability to adapt and endure. The technological vulnerability we've discussed tonight isn't cause for worry as you rest, but rather an invitation to appreciate the delicate balance that makes our modern world possible. The same electromagnetic sensitivity that allows our devices to communicate across vast distances also makes them susceptible to the sun's magnetic moods. Yet humanity has always adapted to the rhythms of our star, from ancient farmers who planted by seasonal light to modern engineers who designed satellites to weather space storms. As you settle deeper into sleep, consider that you are part of this magnificent system, this cosmic dance between star and planet that has been unfolding for 4.5 billion years. The iron in your blood was forged in stellar cores and delivered to Earth by the same solar processes that create space weather. The oxygen you breathe exists because our planet's magnetic field protected the atmosphere that nurtured photosynthetic life. Every heartbeat connects you to this vast electromagnetic symphony that plays constantly between the sun and Earth. In the quiet darkness of your bedroom, charged particles are raining down on our atmosphere. Magnetic field lines are reconnecting in ways that would astonish the greatest physicists, and somewhere above the Arctic Circle, if conditions are just right, ghostly curtains of light are performing their eternal dance. The sun sleeps fitfully, its magnetic field slowly building toward the next solar maximum, when once again coronal mass ejections will race across space to test our planet's protective embrace. This is the world that cradles your dreams tonight, a world shaped by solar flares and magnetic storms, protected by invisible fields, and warmed by nuclear fire, where the dance between chaos and order creates the perfect conditions for life, for consciousness, for the gentle drift towards sleep that carries you now into the peaceful darkness where even the sun's magnetic fury becomes just another lullaby in the cosmic symphony that surrounds us all. The sun. From our vantage point on Earth, it's the most familiar star in the sky, a gentle, golden presence that rises and sets, warming our mornings and stretching shadows into the evening. But 93 million miles away, what looks serene to us is actually a dynamic, boiling ocean of plasma, roiling, pulsing, and exploding with unimaginable energy. Tonight, we're going to drift into that solar sea, not to fear it, but to understand it, and to explore how the sun, especially through its flares, shapes the delicate systems of the world we live in. So, get comfortable. You don't have to watch, just listen. Let your thoughts rise slowly, like sunlight on the horizon. Let's begin. A solar flare is a sudden, intense burst of radiation from the sun's surface. It happens when twisted magnetic fields, tangled like cosmic rubber bands, suddenly snap and realign, releasing energy that's been building up over time. The result? A flash of light, a surge of X-rays and ultraviolet radiation, a wave of charged particles that spreads outward through space. It all begins in the sun's outer atmosphere, the corona, where magnetic fields, shaped by the churning motions of solar plasma, become unstable. These tangled fields can build tension for hours or days, until, in an instant, they break. That break, that snap, is the solar flare. Sometimes it's brief, lasting only minutes. Other times, it can last for hours. But the impact it has, even from 93 million miles away, can be profound. When a solar flare erupts, the radiation it produces travels at the speed of light. That means it reaches Earth in just over 8 minutes. And while we can't see the X-rays or ultraviolet waves, they interact immediately with the upper layers of our atmosphere, especially the ionosphere, a region filled with charged particles. This can disrupt shortwave radio signals, interfere with GPS accuracy, and even affect air traffic communications, particularly near the polar regions. Pilots, scientists, and engineers all monitor solar activity closely, because one powerful flare can create a sudden radio blackout, changing flight paths or temporarily disabling instruments that rely on satellite navigation. But solar flares are only part of the story. Often, they are accompanied by something even more dramatic, a coronal mass ejection, or CME. Imagine the sun not just flaring outward with light, but hurling billions of tons of plasma, charged particles, into space. If one of these solar storms is pointed toward Earth, it can take anywhere from 15 hours to several days to arrive. Unlike the speed of light radiation, CMEs are slower, but potentially much more disruptive. They can buffet Earth's magnetic field, causing what scientists call geomagnetic storms, and what you might recognize as auroras. The northern and southern lights, those shimmering green and purple curtains of light in the sky, are one of the most beautiful side effects of space weather. They happen when solar particles collide with atoms in our atmosphere, oxygen, nitrogen, exciting them and causing them to glow. But those same storms can also create problems. In March 1989, a powerful CME struck Earth and caused a geomagnetic storm that knocked out power across the Canadian province of Quebec. In just 90 seconds, an entire grid failed, transformers melted, currents surged, and the world got a small glimpse of how space, something we usually think of as distant, can reach deep into our daily lives. Modern life depends on systems that are vulnerable to solar flares and CMEs. Satellites, for example, are exposed directly to space. High-energy particles from the sun can damage their electronics, affect their orbits, or degrade their solar panels. Astronauts aboard the International Space Station are protected by shielding, but in the event of a major solar storm, they might retreat to special modules for added safety. Back on Earth, power grids are vulnerable too. Geomagnetic storms induce electric currents in long conductors, like transmission lines and pipelines, sometimes overloading transformers and causing blackouts. Even high-frequency communications, like those used by ships, airplanes, and emergency services, can be disrupted. It's a delicate web, and the sun, with its quiet cycles and sudden outbursts, reminds us just how connected everything really is. So how do we monitor this? Scientists use satellites like the Solar Dynamics Observatory and SOHO, the Solar and Heliospheric Observatory, to keep constant watch on the sun. These space telescopes capture images in ultraviolet light, allowing researchers to track sunspots, flares, and potential ejections before they reach Earth. There are even early warning systems. When a CME is detected, alerts go out to power companies, aviation authorities, and satellite operators. This gives them time, sometimes only minutes or hours, to brace for impact. In this way, space weather forecasting has become as vital as meteorology on Earth. We watch the skies, not just for rain and storms, but for the breath of the sun itself. Solar flares follow an 11-year cycle, a rhythm in solar activity that scientists are still trying to fully understand. Right now, we're heading toward the solar maximum, a peak in this cycle when flares and sunspots become more frequent. That means more auroras, more beauty in the skies, but also more potential for disruption. The dance of solar energy and Earth systems is ancient, it's ongoing, and it's mostly invisible to the naked eye. But it shapes us in ways we're only beginning to measure. And so, as you drift deeper into rest, know that far above you and far beyond, a star is burning, endlessly, beautifully, furiously, sending its light across the void. The same light that warms your skin in the morning also sends storms through the sky. That's the quiet paradox of the sun, a source of life, and, at times, a bringer of challenge, but always, always a mystery worth watching. Now close your eyes, float gently, and let your thoughts follow the solar wind into sleep.